Okay, good evening, Professor David De Los Reyes. Okay, I'm having a full full video format discussion for tonight, and the title of the topic will be alternating current circuit, and this will now be lesson number 18. So for those of you who are following my alternating current circuit long form video format discussion, this is now lesson number 18. Okay, let's proceed. The title of the topic for this evening will be Alternating Current Circuit, lesson number 18. The last time around, we did lesson number 17, and lesson number 17 is a topic on the so-called calculations involving series parallel circuit. Before we will proceed with the next topic, I want to present first this lesson number 18. This is very important because in real life, this is actually the most important thing for parallel circuits. That is the computation of the total current loads that are connected in parallel. The total computation of the total current. Okay, let's proceed. AC circuit, lesson number 18. So I will be presenting tonight 3 impedances in parallel. The problem is only asking for 2 questions, okay, or 2 requirements. Find the total impedance and the total current drawn by the 3 parallel impedances. Okay, let's try to bring out the specs. The load specification, load number 1, the impedance will be designated by Z1. This is 5 minus G3 ohms. Okay. So this is capacitive. For load number 2, instead of giving the current, what is given for load number 2? We are now given the current for load number 2. The current is, the magnitude is 15 amperes, and the angle is negative 45 degrees. This is negative 45. So, if the current is lagging, so this should be an inductive load. It's a coil or a motor load maybe. Right? For number 3, instead of giving the impedance and the current, what is given for load number 3 is the total apparent power. Capital letter S with the subscript 3. The total apparent power for load number 3. This is a very big load. So this could be a load of a business company maybe. The total apparent load for load number 3 is 25 kVA. That's a very big one, meaning 25,000 volt ampere. The power factor is 60%, and the given specs for the power factor, it is lagging. So this still be a motor load maybe. So the first one is a capacitor load. Load number 2 is a motor load. Load number 3 is again a motor load because this is lagging. And here we know that load number 2 is also a motor load because the angle of the current is negative and it is also lagging. This will be the given figure. Load number 1, load number 2, load number 3. This is the utility line, and they are all connected in parallel. That's why impedance is in parallel. 4 to 9. Okay, 3. The requirement of the problem is what will be the total current draw and what will be the total impedance. Total impedance meaning if we try to compress these 3 loads here, okay, what will be Z total equal to? Because if we know Z total, we could compute for the current total. So the key to the solution is to find first the total impedance of the given parallel impedance. Okay, let's try to bring out the solution. For load number 1, Z1 is actually 5 minus G3, right? Capacity. I will try to bring out my calculator. Rectangular. Changing this to polar, so we could determine the magnitude. We divide 3 by 5, trace arctangent. What will come out will be 31 degrees, but it should be negative because this is minus. Take the cosine of this, you divide that to the value of 5, what will come out will be 5.83. Or it will just be simply as a check. Use the Pythagoras principle, 5 squared is 25 plus 9. So that will be, the magnitude should be 34 square root. And the square root of 34 is 5.83. Okay, so you could either use the cosine function, the sine function, or the Pythagoras principle. Still the same, you could compute for the magnitude. It's up to you what method you will be using. Okay, so if we now know Z1, we know the value of this one. We know the voltage across this. Okay, I forgot. The voltage of the power source is 440 volts, angle 0 degrees. This is alternating, the frequency is 6 here. So if we try to compute for I1 now will be the voltage across this. Okay, so it will be B1 over C1. But B1 is equal to the source voltage equal to 440 angle 0 degree. So in polar form, 440 angle 0. Impedance number 1 is capacitive. This is 5.83 magnitude, angle minus 31 degrees. 440 over 5.83 will be 75.45. The angle will be 0. We bring this up, it will now be plus, so this is 31 degrees amperes. So this is actually the plus sign here, meaning the current is leading. For a capacitor, the current is leading. The angle is plus, right? This is plus 31. Okay, let's try to convert this to rectangular form. 31 take cosine multiplied by 75.45, 64.7. 31 take the sine value multiplied by 75.45, that will be 38.81. Okay, so we now know the current passing through load number 1 in terms of rectangular. Okay, so actually we are on the 1/3 portion of the solution. Load number 2, there's no problem with load number 2 because what is given for load number 2, we are now given the current, right? So this problem here got a variation, right? For load number 2, the current is 15 minus 45 degrees amperes. Okay, converting this to rectangular, take cosine of negative 45 times 15, that will be 10.6. Sine and cosine of 45 are the same, so this will be 10.6, 10.6. But since this is minus j 10.6. The value of the real part and the imaginary part, if the angle is 45, are equal. But since this is minus, this should be minus j 10.6 ampere. Okay? And this is also, this is a lagging current. Why lagging? The angle of the current is negative, right? For load number 3, okay, this is where we separate the man from the ordinary man. In general, the product of current and voltage is actually apparent power. The product of voltage times current is actually apparent power, that is EI, right? So if we try to compute for I, it will be volt ampere over E, right? So what is S3? Volt ampere is actually S3, right? So this will now be equal to S3 over V3, and also V3 is equal to E, the source voltage, right? V3 is the voltage across this, equal to the source voltage because the connection is parallel. So converting this kVA, because this is kVA, right? For it to become volt ampere, we multiply that by 1000 over 14 for 40. This is just the absolute value. For the meantime, we do not know the angle yet because later on we must have to bring out the angle of the current. Okay, it's a vector quantity, but we just computed the magnitude from the given apparent power and the voltage. So the magnitude of I3, we know that the magnitude is 56.818 amperes, but what is the angle? We know the angle because the power factor is given, right? One of the definitions of power factor is actually cosine of theta z. Theta z is actually the angle of the impedance, right? So if you take the arc cosine of both sides, the arc cosine of theta z will be theta z, and the arc cosine of the power factor will be the arc cosine of the power factor. Okay, so this should be the arc cosine of the power factor is given 0.6, 60%, 0.6. So if you punch 0.6 press arc cosine, it should be an angle in degrees. It should be 53.13 degrees. 0.6 second function cosine. It's 53.13 degrees. So we have determined already the unknown angle of the load for load number 3 because we are given the power factor, and one of the definitions of power factor is that it is cosine of theta z. So from here we could compute for the angle of the impedance. It should be 53.13 degrees. This is plus and this is plus. So meaning to say this is an inductive load, a motor load, right? And again, if we try to bring out the formula for volt ampere, the product of voltage in current, the product of current times impedance is actually voltage. So current will be voltage over impedance. So I3 now will be B3 over C3. Actually, B3, this is within angle 0 degree, right? And the impedance, we have computed already the angle of the impedance. It is 53.13 degrees, right? We are performing a polar over a polar, right? The value of B3 over C3, we don't have to compute for C3 because the value of B3 over C3 is actually 56.818 already. So the ratio B3 over C3 will be 56.818. Our only problem now is the angle of the current. So if we try to perform this one, we raise it up, right? So the angle will be 0, the angle of the voltage, minus the angle of the impedance. The angle of the impedance is actually a plus, so when it goes up, this will now be minus. That's why the significance of this negative sign here, it is lagging. It was really given that load number 3 got a lagging power factor. So the significance of this negative sign here, it is lagging and it conforms to what is given. So we now know the angle of the current number 3, right? So 0 minus 53.13, it will just be simply negative 53.13. Take the cosine, it will be multiplied by this magnitude, will be 34.1. Take the sine, multiplied by the magnitude, it will be 45.45. But since this is minus, this should be minus. Okay? So we now know the values of I1, I2, and I3 in the so-called rectangular form. And it is very right for the so-called addition of the total current. Because if we try to see the figure, total current will be the sum, vectorial sum of I1, I2, and I3. Vectorial sum. Because current in alternating current circuit are actually vectors. It's a complex quantity. It got a real part and the so-called imaginary part. So substituting the computed values of I1, I2, where's I2? And I3. So this will be the first value of I1, this is the value of I2, and this is the value of I3. So combining all the real parts, 64.7 plus 10.6 plus 34.1, 64 plus 10, that will be 75 plus 34. This is it correct? This should be 109.40. Right? It's almost 100 plus. 64 plus 10, 74 plus 3, that's 100. What comes out is 109. And 38.81 minus 10.6 minus 45.45. The negative thing on the imaginary part is bigger. What comes out is 17.18. The sign is negative. Okay? And to compute for the magnitude of the total current, we convert this real and imaginary to its magnitude value, right? So you press, you divide 17.18 divided by 109.4, okay? You press arc cosine. The resulting angle will be negative 8.92 degrees. Take the cosine of this, you divide that to 109.4, okay? This is negligible compared to this, so this is 110.74 amperes. And the graph of the current is this one. This is I1, this is I2, and this is I3. So the vector sum of I1, I2, and I3 is actually I total. Okay? The angle of I1 with respect to the horizontal is 31 degrees. So this is 31 degrees. The angle of I2 with respect to the horizontal is negative 45. Horizontal line, vertical line, this is negative 45 downward. And the angle of I3 with respect to the horizontal is negative 53.13. So vertical, horizontal, negative 53.13. So this is I1, this is I2, this is I3. So taking the vectorial sum, okay, that will now be I total. And the angle of I total with respect to the horizontal is very small, 8.92 degrees. It's almost horizontal, meaning the power factor is almost 100%. Okay, so we are very good with the utility companies. So this is the total current. Okay, the angle with respect to the horizontal is very small, 8.92 degrees. So if we try to compute for the total impedance, again, voltage is equal to IC, so C total will be B over I. And this is actually E, the utility line voltage, which is equal to B1, B2, and B3. All over the total current, the magnitude is 110.74. So polar form, 440 over 110, that will be 3.925 angle. We raise this up, right? 8.92 degrees. So this is actually an inductive load. The power factor is still lagging, okay? But the resulting triangle will be very small. It will be something like this, right? This is the real part, this is the imaginary part, this is the magnitude, okay? It's almost horizontal because the angle is only 8.92 degrees. Okay? It's almost 92 degrees, and if we try to compute for the power factor, 8.92, take the cosine of that, it's 98.79%. It's almost unity. So your utility companies loves you, right? It's almost unity. The wastage on your what you call this company is very small. The power factor is almost 100%. It's almost 100 efficient. Okay, so for those of you who are taking up electrical engineering, this is for you guys. If you want to share or subscribe to my channel is at youtube.com/@ProfDVJ. If you want to share it, please click share. Okay. The main focus of the problem for tonight is actually the computation of the total current drawn by loads which are connected in parallel, because in real life the connections are actually parallel. So this is very important. So at least we now know how to compute the current. If we are given the impedance, I number 2, there's no problem, the current is given. For load number 3, okay, use your knowledge on the so-called formulas. There are formulas which are needed to compute for the current, because what is given it is not the current. It is the total apparent power and the applied voltage. And from this, we could compute for current number 3. And by using our knowledge of the so-called Complex numbers, we add it vectorially. It's not algebraically meaning real part. You consider all 8 to be real part. No. In alternating current, there is the so-called real part and imaginary part. You must have to segregate the simplification of these two. Okay? This is Professor David J. De Los Reyes. Good evening from Los Angeles.